we have a point A and a point B. So I'm going to sketch these out. Honestly, I think always a good shout with these vector questions is to just sketch out what's going on. So this is O, A, and B, and then we're told that the position vector point A is 7, 2, minus 7. And for B, we've got 12, 3, minus 15. And then find a vector for the line L1, which passes through A and B. So this here is L1. Okay, our standard approach for this is to, right, we're gonna try and find like a general point R that is along L1. This is the vector equation of the line. And first of all, we're going to get onto the line, so we can go along A or along B. I'll go along A, doesn't matter. And then once I've got onto the line, I need to just go along some amount here, and that would get me, if I go up here red and then along here green, I'm going to get to this point R. Or sorry, the vector. I would equivalently have gone along the vector R. Now that means I need to work out what AB is, and AB is minus OA plus OB. So it's 12, 3, minus 15, minus 7, 2, minus 7, which gives 5, 1, and that's going to be minus 8. So we're nearly there. Now we just need to say, hey, we're going to go along some amount of that from A to B. Call that, say, T. And that is our answer. Note, you could replace this 7, 2, minus 7 with 12, 3, minus 15. It would still be the vector equation of the line. It would just be, you need a different value of t to get to where you need to. You could even, you could do BA instead and swap this around. So there's actually, more than one option. Looking up now, we have another vector equation of a line. So this is for L2. And we're asked to show that L2 passes through the origin. I'm going to write it in component form. So remember, it's I, J, K. And I can see that the y coordinate will be 0 everywhere, in fact, along this vector. How do I get the x coordinate is 0? Well, if I set mu equal to 0, sorry, it's equal to 4, when mu equals 4, r will equal minus 4 plus 4, 0, and 12 minus 12, which is 0, 0, 0. Okay, nice one. Moving on, we're then asked to show that L1 and L2 intersect at a point C and to find that point. So if L1 and L2 intersect, their position vectors will be equal. So 7 plus 5t must equal minus 4 plus mu. And then the y part's 2 plus t must equal 0. Minus 7 minus 8t must equal 12 minus 3 mu. So straight away, we get that t is going to equal minus 2. And if I substitute this into here, then I would get 7 minus 10 equals minus 4 plus mu. That's going to be minus 3 or plus 4. Mu must equal 1. And I just need to now check that it's consistent with this. So the left-hand side will equal minus 7 plus 16, which is 9. And the right-hand side equal 12 minus 3, which is also 9. So consistent solution. L1 and L2 intersect. And to find out where they intersect, we just need to substitute in for one of these. So mu equals 1 is going to be the easiest thing to substitute in. So we'll get minus 4, 0, 12. Plus 1, 0, minus 3. Set mu equal to 1, which gives me minus 3, 0, 9. So I can say they intersect at this point, because technically that's a vector. Okay, good work. Right, A, B, and C are done. We're now asked to find the cosine of angle OCA. I'm just going to sketch this out, OCA. Well, we have line 1 and line 2, and they intersect at point C. That's the point that we just found. We know that line 2 goes through the origin, so that's going to be O, and L1 goes through A and B, but we're specifically interested in OCA, so this angle here. And we can investigate the angle using the dot product. So that would be CO dotted with CA. You always take the vectors that are going out from the point. Okay, well, we just calculated OC because it was the position vector of the point of intersection. It was that minus 3, 0, 9. And so CO is going to be 3, 0, minus 9. That just leaves us to needing to find CA. C to A, well, we can go along CO and then along OA. So that'll be 3, 0, minus 9 plus. And this takes us back to A right at the start of the question. Here it is, 7, 2, minus 7. So this gives us 10, 2, and minus 16. Now back to the dot product. Remember, there's two ways of using the dot product. We can either write it down as the magnitude of CO times the magnitude of CA times cos of angle OCA. Or we can basically multiply, so x1, x2 plus y1, y2 plus z1, z2. We can multiply the components accordingly. So I'm going to write down is 3, 0, minus 9. Dotted with 10, 2, minus 16. That's going to equal 30 plus 9 times 16, that's 90 plus 54, that's 144. Just before I do any more, I'm going to work out separately the magnitudes. So the magnitude of CO. For this, I can use 3D Pythagoras. So it's going to be 3 squared plus 0 squared plus minus 9 squared, square rooted. (81 plus 9 is 90. And the magnitude of CA will be 10 squared plus 2 squared plus minus 16 squared. And that's going to be 100 plus 4 plus 256. Worth knowing that that's what 16 squared is. That's 206, 360. And so this thing here is going to equal root 90 times root 360 times cos angle OCA. And that gives me 174 equals, or I've got 90 times 360. Now I could write it as root 9, root 10 times root 36, root 10. This will allow me to multiply it much easier, times cos of angle OCA. So this equals 3 times root 10 times root 10 gives me 10 times 6. And that's going to give me 180. So I can divide by it. And I can cancel it down. So I think I'll divide by 2. 2's into 174. We'll go 87 over 90. Now 3 goes into both of these. So finally, cos of the angle is going to be 29 over 30. Okay, part E, we're getting there. Hence or otherwise, find the shortest distance from O to L1. The hence is a big clue. So let's just look at the diagram we had before. That was all the way up here, might actually borrow that. So the shortest distance, O to L1, is going to be if we take the perpendicular from it. Rather than going like off at an angle, you know, over here or something, go to 90 degrees. This is a bit like if you had a triangle and you wanted the nearest point to the bottom, well, you wouldn't go like off down here, would you? You would go at 90 degrees. So we constructed a 90-degree angle. And what else do we know? We know the length of OC. We calculated that, and it was root 90. So if we want to work out this one, this is the opposite. We're going to need sine of angle OCA. Well, we have cos of angle OCA. So we can draw a little triangle down here. It's not the same picture, but it's kind of the right sort of ratios. So this is angle OCA and cos, so it's going to be 29 here and 30 here. And now we can work out this length, and that will allow us to work out sine. So 30 squared minus 29 squared, square rooted, that's going to give us this missing length. You could work these out, but actually there's a really nice trick. This is a difference of 2 squares, so it's 30 minus 29 times 30 plus 29 square rooted, so it's root 59. And therefore sine of angle OCA is root 59 over 30. That's going to be useful because over here we have the same thing. So root 59 over 30 for this triangle is going to be question mark over root 90. And therefore OL, sorry, it's not OL, is it? I don't know what point this is. I'll call it the shortest distance. It's going to equal root 59 over 30 multiplied by root 90. maybe it's fine to leave it like that. I think we can cancel it down. So we could write it as root 59. I can see a root 30. This is 30 times 3, so root 3. And over here, I've got root 30, root 30. So these will cancel. That root 3 will cancel partially with this to leave me with root 10. So I could write it finally as a single fraction, root 59 over 10. That is the shortest distance from L1 to the origin. Okay, brilliant. Keep going. There are a lot of parts to this question. Right, all the way back to the top. Okay, we're now asked to show that CO is equal to AB. Well, we already calculated CO. Where was it? It was root 90. So we just need to show that AB is also root 90. Okay, so AB. Well, I think we worked out what AB was actually, didn't we? So that's what it was. It was this 5, 1, minus 8. Sorry, I realized I said minus 8 and I wrote minus 6. 25, so 5 squared plus 1 squared plus minus 8 squared. That is also equal to root 90. Okay, and we are done. Presumably this might come into the very last part. Here it goes. So in the final part, we're asked to find a vector equation for the line that bisects angle OCA. Now I'm going to draw a little sketch as before to try and visualize what's going on. This time I'm going to put L1 here and L2 here. So I've made it horizontal. And then this point is C. And I'm interested in this line that bisects. Remember, I also know that L2 goes through the origin. And what I can do is I haven't put A and B in. Okay, I don't know exactly where they are. But what I can now do is essentially construct a rhombus. So I can make this CO. I can go along parallel to L1. And then parallel to L2. And it must be that all of these sides are the same length. I've basically chosen this point here. So C to it is the same as CO. And then if I go parallel to L2 and parallel to L1, like that will necessarily work out because it is bisecting. And I'm going to label this point X. So the aim is going to be to get onto the line from O, which we can do using OC. And so I just need the vector CX, because then we can go along, however much we want of CX, like double 2 lots of CX or half lots of CX and so on. Now CX is going to be equal to CO plus OX. But here's the neat bit. We have that AB, remember the magnitude is equal to the magnitude of CO. So OX, which is the same length, must also be the same as AB. The way we've constructed it, so this is parallel to this, and these two are parallel. Therefore, CX is CO plus AB. That result was absolutely crucial from before. And remember, we have what CO is. Can't remember where it's gone. Okay, here's AB. So 5, 1 minus 8. And CO is 3, 0 minus 9. Which gives us 8, 1, and minus 17. So all we need to do for the equation is to get onto the line, which we can do using OC, which is going to be minus 3, 0, 9, plus some constant multiplied by CX. Okay, I don't think that's easy personally. Especially, it's all about getting the construction right. But that is the final answer. Well done if you managed that.